Hello everyone. In this session we are going to study about standards of volumetric analysis. So volumetric analysis is basically the titrimetric analysis. So first of all, just have a look at the setup of the titrimetric assembly. So in the diagram you can see the burette which contains your titrant, that is NaOH, conical flask which contains the sample. For example, suppose that we are determining the concentration of H2SO4. In the conical flask we will add indicator which will give the color change at the end of the reaction. So as you can see here, titrant is NaOH, our sample, it is known as titrate, it is H2SO4, and indicator is phenolphthalein. So you can see here that NaOH is the standard solution, but we know NaOH is susceptible to atmospheric condition. It absorbs carbon dioxide from the air and it is unstable for a very longer period of time. So we need to standardize the NaOH with help of some other standard substance. So here NaOH is our secondary standard because it needs to be standardized before using it for estimation of the acid. And the substance which is used for standardization of NaOH, it is known as primary standard. Why it is necessary to standardize NaOH? Now suppose we have prepared the solution of NaOH as 0.1 normal. Now if we perform the titration of H2SO4 with 0.1 normal NaOH at the next day, then there are chances that NaOH may absorb carbon dioxide from the air and its concentration may deviate from 0.1 normal. So in the calculation, if we use the concentration of NaOH as 0.1 normal, then it may give false result for sulfuric acid because the concentration of NaOH has deviated from 0.1 normal. So we need to standardize NaOH just before the titration, and this can be done with the help of primary standard. So we will see one by one what is exactly primary standard and what are secondary standards. Primary standard, it is a substance of high purity and they are used to determine the concentration of other solutions to an extremely high accuracy. What are the requirements for primary standard? They must be easy to obtain, purify, dry, and to preserve in pure state. They should be almost 100% pure. They must be stable to atmospheric conditions, that is, they must not decompose or must not be hygroscopic or deliquescent. Hygroscopic means absorption of moisture from the air, and deliquescence means absorption of moisture from the air and subsequently getting converted to liquid. So whichever primary standard we use, it must be stable to atmospheric condition, that is, it must not decompose or it must not be hygroscopic or deliquescent. It should also not have any water of hydration. If it will have water of hydration, it may lose it when exposed in air for the longer time. Also, the primary standard should be readily soluble and it must have high molecular weight to reduce the effect of weighing error. Let us see some examples of primary standard. For acid-base titration, sodium carbonate. In complex formation reaction, that is in complexometric titration, often zinc and magnesium are used as primary standards. In precipitation titration, silver and silver nitrate are used as primary standard. In redox titration or redox reactions, potassium dichromate is used as primary standard. So secondary standards, it is prepared in the laboratory for specific analysis. For example, just we have seen the example, like for estimation of H2SO4 we use NaOH. So NaOH has been prepared for specific analysis, that is for analysis of H2SO4, but it is not stable in its own form. Hence it must be standardized against a primary standard before use. Properties of secondary standard: it is less pure as compared to primary standard. It is less stable and more reactive than primary standard. But when converted in the solution form, it can remain stable for the longer time as compared to its solid form, and it must be titrated against primary standard. If we use the secondary standard without standardization for estimation of some sample, then it may lead to error in our result. So this was about primary and secondary standards. Now let us have a look on how to prepare and standardize solutions. So first of all, let us see NaOH. Now if we want to make the solution of particular molar, then we must know the molecular weight of the sample. And if we need to prepare the solution of particular normality, then we must know the equivalent weight of the sample or our substance, because during calculation of molarity we take into consideration molecular weight, and during consideration of normality we take into consideration equivalent weight. The molecular weight and equivalent weight concepts have been discussed in our previous sessions. So molecular weight of NaOH is 40 gram per mole. Its acidity, that is number of reproducible OH group, is 1. Hence its equivalent weight is same as that of molecular weight. So equivalent weight of NaOH is 40 gram per mole. Now suppose we need to prepare 0.1 molar NaOH, then we need to dissolve 4.20 gram of NaOH in water and make up the volume to 1000 ml. Now NaOH tends to absorb carbon dioxide from the air. So during its preparation, carbon dioxide free water must be used. So how this can be done? This can be done by boiling water for a few minutes and protecting it from atmosphere during cooling and storage. Its standardization can be done against 0.1 normal oxalic acid, because oxalic acid is a primary standard, and indicator which is used is phenolphthalein. So normality of NaOH can be determined with help of formula N1V1 is equal to N2V2. Now we know normality of oxalic acid. We can note down the burette reading, that is how much ml of oxalic acid has reacted with the NaOH. Suppose it is 10.2 ml. And sample our NaOH we have taken 10 ml. So by keeping all the values we can calculate normality of NaOH. So next sample is potassium permanganate, that is KMnO4. KMnO4 behaves differently in various mediums like acidic, basic and neutral. So in acidic medium, let us have a look at the reaction. KMnO4 reacts with sulfuric acid to give manganese sulfate, potassium sulfate. So here valency of manganese changes from +7 to +2. So the difference is 5. So N factor for this reaction is 5. So we can calculate equivalent weight by molecular weight divided by N factor. The molecular weight for KMnO4 is 158 gram per mole. So equivalent weight in acidic medium will be 158 divided by 5. Because in acidic medium change of valency takes place from 7 to 2, that is difference is 5. So in acidic medium equivalent weight is 31.6 gram per equivalent. In faintly alkaline or neutral, manganese valency of manganese changes from +7 to +4, that is gain of 3 electrons. So equivalent weight will be molecular weight divided by 3, that is 52.67. In highly alkaline medium, valency changes from +7 to +6. There is gain of only 1 electron, and hence here equivalent weight will be same as that of molecular weight, that is 158 gram per equivalent. So while preparing KMnO4, we must take into consideration that which medium is used for its preparation, that is alkaline, neutral or acidic. So let us have a look at the preparation of 0.1 molar potassium permanganate solution. So weigh 0.33 gram of KMnO4 and transfer it in a beaker and dissolve in 20 ml of water by stirring. See, KMnO4 is not very easily soluble, so continuous stirring is required. Now transfer the supernatant to 100 ml volumetric flask and add another 20 ml of water to beaker which contains undissolved KMnO4. Again stir to dissolve and transfer the supernatant to volumetric flask. So this process has to be repeated until all the crystals of KMnO4 dissolve. And finally make up the volume to 100 ml with water. We have to store the solution in the dark or diffuse light or keep it in the dark brown glass bottles because KMnO4 is susceptible to light. Standardization can be done against oxalic acid. We have to add in it 5 ml of dilute sulfuric acid, warm it at 60 to 70 degrees Celsius and titrate against KMnO4. Now remember, KMnO4 acts as a self-indicator. At the end point, the color changes from colorless to pink because KMnO4 is pink. So the excess drops of KMnO4 will impart pink color to the solution. So there is no need of external indicator. KMnO4 can act as a self-indicator. Now suppose 10 ml of 0.1 normal oxalic acid has reacted with 9.75 ml of KMnO4. So by keeping all the values, we can find out normality of potassium permanganate. Sodium thiosulfate, its molecular weight is 258 gram per mole and equivalent weight is 248 gram per mole, that is both are same. So dissolve 24.8 gram of sodium thiosulfate and 200 milligram of sodium carbonate in 1000 ml of recently boiled and cooled water. It can be standardized against dimethyl potassium dichromate. Here are also added 3 gram of potassium iodide, 2 gram of sodium bicarbonate and 5 ml of hydrochloric acid. We have to allow the solution to stand in dark for exactly 10 minutes. We have to rinse the stopper and inner walls of the flask with water and titrate the liberated iodine with sodium thiosulfate solution until the solution is yellowish green in color. Then we have to add starch as the indicator and we have to continue titration until the blue color is discharged. Also blank titration, that is without the sample, has to be performed. Normality can be calculated from the given formula. HCl, its molecular weight is 36.46 gram per mole. It's dense, so for 1 normal we need to dissolve 36.46 gram of HCl. But HCl is in ml, so we need to convert the gram into volume. So volume is equal to mass divided by density. So volume of HCl comes out to be 30.67 ml. But as concentration of HCl is 37.5%, so actual volume will be 81.78 ml. And we have to make up the volume to 1000 ml. It can be standardized against anhydrous sodium